1. The Antikythera mechanism. In 1901, off the coast of the Greek island of Antikythera, sponge divers exploring a shipwreck 70 feet below the surface discovered a corroded bronze artifact that would challenge everything historians believed about ancient technology. The object, encrusted with marine growth and shattered into fragments, appeared to be a complex arrangement of gears, dials, and inscriptions. It would take over a century to understand what they had found. The ship had sunk around 70 BCE, carrying luxury goods, statues, and scientific instruments. Among the cargo was this device, later named the Antikythera mechanism, a bronze machine approximately the size of a shoebox containing at least 30 interlocking gears. Initial examinations dismissed it as an astrolabe or navigational tool, but X-ray analysis decades later revealed something far more extraordinary. The mechanism was a computer, an analog calculator designed to predict astronomical positions, eclipse cycles, and the movements of celestial bodies with stunning accuracy. The gear ratios encoded the Metonic cycle, a 19-year pattern governing lunar phases, the Saros cycle, predicting eclipses over an 18-year period, and the Callippic cycle, a 76-year astronomical calendar. The front dial displayed the zodiac and the Egyptian calendar. The rear dials tracked lunar months, eclipse predictions, and the dates of athletic games like the Olympics. Inscriptions provided operating instructions, describing how to input dates and interpret the outputs. The precision of the gears, some with teeth smaller than a millimeter, suggested manufacturing techniques not seen again until the 14th century. When researchers reconstructed the mechanism using modern imaging and computational modeling, they discovered it could calculate planetary positions, predict solar and lunar eclipses years in advance, and adjust for the irregularities in the moon's orbit caused by its elliptical path. The mathematics required for this device would not be formalized in Europe for over 1,000 years. But the most disturbing aspect was not what the mechanism could do. It was the implication of what had been lost. This was not a prototype. The sophistication of the design, the miniaturization of components, and the complexity of the gear trains suggested a long tradition of mechanical engineering that existed in the ancient world and then vanished without a trace. Now, no comparable device has been found from antiquity. No texts describe how it was built, and no direct lineage connects the Antikythera mechanism to later European clockwork. The knowledge simply disappeared, as if an entire field of engineering was erased from history. Modern attempts to recreate the mechanism require advanced machining tools, yet ancient craftsmen produced it using hand tools and techniques that remain partially mysterious. Some researchers believe the device was one of many, that workshops across the Hellenistic world produced similar machines for astronomical research, education, and navigation. If true, then hundreds of these computers may have existed, all lost to corrosion, looting, and the collapse of civilizations. The shipwreck that preserved the mechanism was a stroke of luck. Had the bronze not been submerged in seawater, it would have been melted down and repurposed, as happened to countless ancient artifacts. What survives is a fragment, a glimpse of a technological capability that should not have existed 2,000 years ago. If the Greeks built computers, what else did they create that history forgot? And why did this knowledge vanish so completely that its rediscovery required 2 millennia of scientific progress? 2. The Baghdad Battery. In 1936, near the village of Kujut Rabu outside Baghdad, German archaeologist Wilhelm König excavated clay jars dating to approximately 200 BCE. Each contained a copper cylinder, an iron rod, and traces of an acidic substance. König proposed a controversial theory. These jars were ancient batteries. The construction was deliberate. The copper cylinder was sealed at the bottom with asphalt. The iron rod was suspended inside without touching the sides. When filled with an electrolyte, the jars generated approximately 1 to 2 volts per cell. Multiple jars connected in series could produce higher voltages. König speculated the batteries were used for electroplating. Ancient jewelry from the region showed gilding so fine that modern jewelers struggled to replicate it without electrical assistance. Replicas of the Baghdad battery, using identical materials, successfully generated electricity. When filled with vinegar, the jars produced enough current to plate small objects with gold in hours. But skeptics argued the jars were storage vessels, that copper, iron, and acidic residue was coincidental. No ancient texts mentioned batteries. Yet multiple jars were found in similar configurations. The copper cylinders were carefully rolled and soldered. The asphalt seals suggested intentional insulation. In 1978, Egyptologist Arne Eggebrecht electroplated a silver statuette using reconstructed batteries. The process worked flawlessly. Eggebrecht concluded ancient civilizations possessed practical electrochemistry knowledge, even without theoretical framework. The Baghdad battery disappeared during the Iraq War. Looters ransacked the National Museum in 2003, and the original jars were lost. What remains are photographs, drawings, and the question of what the Parthians understood about electrical phenomena. If ancient peoples harnessed electricity, what other technologies were developed and forgotten? Now, the absence of written records does not mean knowledge did not exist. It may simply mean it was transmitted orally, through apprenticeships, in methods leaving no archaeological trace. 3. Greek fire. In 678 CE, during a naval siege of Constantinople, the Byzantine fleet unleashed a weapon so devastating it turned the war's tide. The substance, Greek fire, ignited on contact with water, burned on the sea's surface, and could not be extinguished by conventional means. Enemy ships caught in its flames were consumed entirely. The formula was history's most closely guarded secret. Only the ruling emperor and select chemists knew its composition. Knowledge was passed through a single family, descendants of Callinicus of Heliopolis. Production occurred in sealed workshops under armed guard. An unauthorized disclosure was punishable by death. The weapon was deployed using bronze siphons mounted on warship prows. Pressurized liquid fire sprayed across distances exceeding 50 feet, coating vessels in flames water could not douse. The psychological impact was overwhelming. Opposing fleets fled at sight of Byzantine ships with raised siphons. For over 500 years, Greek fire gave Byzantium naval supremacy. Arab fleets attempting to capture Constantinople were annihilated. Viking raiders targeting coastlines were incinerated. But the composition has never been definitively determined. The Byzantines left no written formula. When the empire fell in 1453, the knowledge died with the chemists. Modern reconstructions have approximated effects but never replicated exact properties. The sustained combustion, resistance to extinguishing, ability to adhere like napalm. The loss represents more than a military secret. It signifies knowledge transmission's fragility. A single family guarded the formula for generations, and when that lineage ended, the secret vanished. The technology defending an empire for half a millennium simply ceased to exist. If Greek fire was intentionally obscured to prevent enemy acquisition, the strategy succeeded too well. The Byzantines protected their weapon so thoroughly that even their descendants could not recover it. 4. Damascus steel. In the 11th century, swordsmiths in Damascus produced blades of extraordinary quality, renowned for sharpness, flexibility, and distinctive wavy patterns. These swords could slice through European broadswords, cut falling silk scarves, and maintain edge through years of combat. The method of creation remains metallurgy's greatest mystery. The blades were forged from wootz steel, produced in India and Sri Lanka. The material contained high carbon levels, between 1 and 2%, with trace impurities of vanadium, molybdenum, and chromium. When heated, hammered, and folded repeatedly, these elements formed microscopic carbide structures, creating composite material harder than the surrounding iron matrix. The surface patterns were not decorative. They were internal crystal structures made visible, cementite nanowires and carbon nanotubes aligned within metal at scales invisible to the naked eye. Modern electron microscopy confirmed Damascus steel contained carbon nanotubes, shocking materials scientists, as these structures were believed exclusive to late 20th century nanotechnology. The swordsmiths did not understand atomic mechanisms. They refined techniques through centuries of trial and error, passing knowledge from master to apprentice. They knew which ores produced best results, precise temperatures for forging, and fold numbers needed for optimal strength. By the 18th century, true Damascus steel production had ceased. Reasons remain unclear. Some suggest specific ore deposit depletion. Others propose trade route changes, political instability, or master-smith loss through war. Numerous recreation attempts have been made over 3 centuries. Metallurgists analyzed surviving blades, identified chemical composition, replicated forging techniques. Some produced blades with similar patterns and performance, but none conclusively reproduced exact microstructure of original Damascus steel. The challenge lies in precision required. Temperature variations of even a few degrees alter carbide formation. Impurities impossible to standardize before industrial refining play critical roles. The heating, hammering, and cooling rhythm must follow patterns developed through intuition rather than measurement. If Damascus steel was accidental empirical refinement, it suggests advanced materials can emerge from craft traditions without requiring scientific theory. And if such materials were produced then lost, it raises the question of what other technologies existed in pre-industrial societies, functional and effective, yet unrecognized and unpreserved. 5. Roman concrete. In 27 BCE, Roman engineers completed the Pantheon in Rome, a temple featuring a massive unreinforced concrete dome spanning 143 feet. The structure has stood over 2,000 years, enduring earthquakes, floods, and centuries of weathering. Modern concrete often begins deteriorating within decades. The Romans possessed a formula surpassing contemporary materials, and its durability secret was lost for over a millennium. Roman concrete, opus caementicium, was composed of lime, volcanic ash, seawater, and aggregate. The volcanic ash from deposits near Mount Vesuvius and Pozzuoli contained aluminosilicate minerals reacting chemically with lime and seawater to form exceptionally strong binder. The durability is remarkable. Harbor installations built 2,000 years ago remain intact, submerged in seawater, subjected to constant wave action and salt corrosion. So modern concrete in similar conditions disintegrates within 50 years. Recent analysis revealed Roman concrete is not static. It continues strengthening over time. When seawater infiltrates, it reacts with volcanic ash, forming crystalline minerals filling microscopic cracks. The concrete self-heals, growing denser with age. This pozzolanic reaction occurs because volcanic ash contains reactive silica and alumina bonding with calcium hydroxide in lime. The Romans did not understand chemistry. They knew empirically that volcanic ash from certain regions produced superior concrete, that seawater enhanced mixture, and that slow curing improved strength. They documented techniques in texts like Vitruvius's De Architectura. After the Western Roman Empire's fall in the 5th century CE, knowledge faded. Medieval builders lacked volcanic ash access, and lime production techniques declined. Construction reverted to stone and timber. When concrete reemerged in the 18th century, it was different, based on Portland cement, lacking self-healing properties. Modern engineers have attempted recreation using Italian volcanic ash and seawater. Results are promising. Laboratory tests show replicated Roman concrete exhibits similar durability and self-healing. But scaling production presents challenges. Volcanic ash is not readily available, and slow curing conflicts with contemporary timelines. The irony is inescapable. The Romans, 2,000 years ago, built structures more durable than modern infrastructure using techniques considered primitive. They achieved this without advanced machinery, chemical analysis, or materials science understanding. They observed, experimented, and refined over generations. If Roman concrete was superior, then progress is not linear. Civilizations possess knowledge, lose it, and spend centuries recovering what was once routine. 6. The precision of Saqsaywaman. In the mid-15th century, high in the Andes above Cusco, Inca engineers constructed Fortress Saqsaywaman. The site features massive stone walls from blocks weighing up to 200 tons, cut and fitted with such precision that a knife blade cannot slide between them. No mortar was used. Stones interlock through geometry alone. The largest blocks were quarried miles away, transported across mountainous terrain, and lifted into position using debated methods. Stones are uniquely shaped, though with irregular polygonal faces designed to fit perfectly against neighbors. Cuts follow deliberate patterns, distributing weight evenly, preventing earthquake shifting, creating structural stability superior to mortared masonry. Modern stonemasons express disbelief. Tolerances achieved by Inca craftsmen are comparable to precision machining. Surfaces align within fractions of a millimeter across contact areas spanning several square feet. Angles match so closely that joints are nearly invisible. How this was accomplished without metal tools, wheeled vehicles, or written blueprints remains unclear. The Inca used bronze and stone tools, neither capable of cutting andesite, the volcanic rock composing many blocks. Andesite ranks between 6 and 7 on Mohs hardness scale. One theory suggests using harder stones like diorite hammers to pound softer andesite sections. Experimental archaeology demonstrates this technique works, but is labor-intensive, requiring months per block. For thousands of precisely fitted stones, timelines stretch into decades or centuries. Another theory proposes plant-based acids or chemical softening agents. Some researchers point to Andean plants containing oxalic acid etching stone over time, but no evidence supports widespread chemical treatment use. A controversial hypothesis involves thermal manipulation. Heating stone to high temperatures, then rapidly cooling with water, causes fracturing along crystalline boundaries, allowing controlled splitting. But it does not account for precision shaping of contact surfaces. What complicates all theories is the absence of tool marks. Modern cutting leaves, visible scratches, grooves, or percussion patterns. Saqsaywaman stones show remarkably smooth surfaces. The earthquake resilience is equally remarkable. Cusco, in a seismically active region, has experienced numerous major earthquakes. Colonial buildings were repeatedly destroyed. Saqsaywaman's walls remained intact. Interlocking stones shift during tremors, absorbing and dissipating energy, then settle back. Modern attempts to recreate Inca stonework using traditional tools have achieved limited success. Replicas lack original precision, and time required makes such construction economically unfeasible. If a civilization without written language, without the wheel, and without iron tools could achieve masonry precision matching modern machining tolerances, then the relationship between technology and capability is more complex than assumed. 7. Archimedes' death ray. In 212 BCE, during the Roman siege of Syracuse, Greek mathematician Archimedes reportedly devised a weapon capable of setting enemy ships aflame from a distance. According to ancient accounts, Archimedes arranged bronze mirrors along city walls, focusing sunlight onto approaching Roman vessels. Concentrated solar radiation ignited wooden hulls, forcing fleet retreat and prolonging siege for months. The story has been debated for centuries. Skeptics argue focusing sunlight with ancient mirrors would be impractical, requiring precise alignment, stable weather, and stationary ships long enough for combustion. But ancient sources describe the event in detail. Historian Lucian, writing in the 2nd century CE, now stated Archimedes set the ships of the enemy on fire with his burning glasses. Byzantine scholar Anthemius of Tralles referenced Archimedes' mirror use for military purposes and conducted his own replication experiments. Modern recreations have produced mixed results. In 1973, Greek engineer Ioannis Sakkas arranged 70 bronze-coated mirrors focusing sunlight onto a wooden boat 160 feet away. The vessel ignited within minutes. MIT students in 2005 achieved comparable results, though ships had to remain stationary with ideal weather. Feasibility hinges on ancient mirror quality. Polished bronze or silver can reflect up to 70% of incident sunlight. If Archimedes deployed dozens of large mirrors simultaneously, cumulative energy focused onto a single point could exceed dry wood ignition temperature, approximately 450 degrees Fahrenheit. But logistics present challenges. Aligning multiple mirrors to focus on moving targets requires coordination and rapid adjustment. Ancient accounts do not describe aiming mechanisms. Some reconstructions suggest Archimedes used parabolic arrangements to concentrate sunlight automatically as ships entered focal zones. Archimedes' writings on optics are partially lost. His mirror treatise, mentioned by later scholars, has not survived. Principles he employed, including reflection law and parabolic curve properties, were within his mathematical capabilities. Whether functional or exaggerated, the death ray represents theoretical knowledge applied to practical warfare. Archimedes understood that light behaves predictably, mirrors redirect and concentrate solar energy, and sufficient heat ignites combustibles. When Romans breached Syracuse's defenses, they were ordered to capture Archimedes alive. Instead, a soldier killed him, allegedly because Archimedes refused to interrupt mathematical work. His death marked an era's end. Siege engines, mirrors, and inventions defending Syracuse were dismantled or lost. If Archimedes truly built a solar weapon, then the boundary between ancient and modern technology is narrower than assumed. And if such knowledge was lost because a single man died before passing it on, then history is shaped as much by fragile knowledge transmissions as by inventions themselves. 8. Ancient Indian flying machines. In Vedic texts of ancient India, composed between 1500 BCE and 500 BCE, detailed descriptions appear of aerial vehicles called vimanas. Texts including the Ramayana, Mahabharata, and Vaimanika Shastra describe crafts capable of flight, maneuverability, and speeds exceeding anything achievable by known ancient technology. The Ramayana describes Ravana's Pushpaka Vimana as a celestial chariot, flying at great speeds, carrying multiple passengers, traveling vast distances. The Mahabharata references Vimanas in warfare, launching projectiles, maneuvering through aerial combat. The Vaimanika Shastra provides detailed schematics, construction methods, and operational instructions. According to texts, Vimanas were powered by mercury vortex engines, devices using rotating liquid mercury to generate thrust. The Vaimanika Shastra describes the Rukma Vimana, built from special heat-resistant metals, equipped with controls for ascending, descending, and changing direction. Skeptics dismiss texts as mythology or retroactive fabrication. Ancient peoples lacked metallurgy, engineering knowledge, and energy sources for powered flight. But some researchers have taken descriptions seriously, attempting to decode technical language and reconstruct devices. In 1952, Sanskrit scholars and aeronautical engineers analyzed the Vaimanika Shastra, translating technical terminology and comparing to modern aviation principles. They concluded the text described advanced concepts including gyroscopic stabilization, retractable landing gear, and propulsion resembling ion drives or magnetohydrodynamics. Mercury vortex engines have intrigued researchers. The concept involves rotating mercury at high speeds within sealed chambers, generating magnetic fields theoretically producing lift or thrust. Modern physics recognizes rotating conductive fluids create electromagnetic effects, though harnessing for propulsion remains experimental. Archaeological evidence for Vimanas is non-existent. No remnants of ancient aircraft, propulsion systems, or flight operations infrastructure have been discovered. The absence of physical evidence leads mainstream academia to reject literal interpretation. Yet texts remain detailed, technical, and consistent. They describe vehicles with specific dimensions, materials, and operational characteristics. They reference metallic alloys, energy sources, and engineering principles not formalized in Western science for millennia. If Vimanas were purely mythological, why include technical specifications? Mythology typically emphasizes narrative, not engineering schematics. Inclusion of construction details, material properties, and operational instructions suggests texts served purpose beyond storytelling. One possibility is that texts preserve fragmented knowledge from an earlier, more technologically advanced period, transmitted orally for generations, then written with embellishments. Another is that ancient Indian scholars possess theoretical understanding of flight, propulsion, and mechanics they could not practically implement, but documented nonetheless. If Vimanas existed, even in prototype form, implications are profound. Human flight was achieved not in the 20th century CE, but potentially 3,000 years earlier, then lost, forgotten, and rediscovered only through slow accumulation of Western scientific knowledge. 9. The Dendera light bulbs. In the Temple of Hathor at Dendera, Egypt, built during the Ptolemaic period around 50 BCE, stone reliefs depict objects sparking intense debate. Carvings show elongated, bulb-shaped objects connected to braided cables, supported by pillars resembling insulators, containing wavy serpent-like figures inside. To some observers, images unmistakably resemble modern electric light bulbs. The reliefs are located in crypts beneath the temple. Walls are covered with hieroglyphics describing rituals, offerings, and symbolic significance. Bulb-like carvings appear alongside priests, deities, and sacred ceremonies, suggesting religious or functional importance. Mainstream Egyptology interprets images as mythological symbols. Elongated bulbs represent lotus flowers or Deuged pillars. Serpents signify divine energy or creation myths. Braided cables are cosmic forces symbols. Carvings are purely allegorical. But alternative researchers argue symbols are too specific to dismiss. Objects are proportioned like electrical devices. Serpents resemble plasma arcs or electrical discharges. Supporting pillars match ceramic insulator design. Braided cables could represent conductors. In 1978, Austrian engineer Walter Garn and German Egyptologist Peter Krasse proposed reliefs depicted functional electric lamps powered by primitive batteries. They suggested ancient Egyptians used electricity for illuminating dark temple interiors. Engineers built Dendera bulb replicas based on relief carvings. Devices were constructed using glass tubes, metal electrodes, and inert gases. When connected to power, they produced light through gas discharge, similar to modern fluorescent lamps. The experiment demonstrated carved objects could function as light sources if supplied with electricity. Critics countered Egyptians had no need for electric lighting. They used oil lamps, torches, and reflective mirrors. Absence of ceiling soot, often cited as evidence for artificial lighting, could be explained by ventilation or clean-burning oils. No archaeological evidence supports ancient Egyptian electrical systems, no wiring, generators, or power sources found. Yet Dendera carvings remain enigmatic. If purely symbolic, why depict objects with engineering-like detail? One explanation is convergent symbolism. Shapes coincidentally resemble modern technology but originated from different cultural contexts. Another is that carvings depict real objects whose function has been misunderstood. Perhaps Egyptians built ceremonial lamps using natural phosphorescent materials, bioluminescent organisms, or chemiluminescent reactions. A third explanation is that ancient Egyptians possessed limited electrical knowledge, possibly through contact with other civilizations, experimentation, or accidental discoveries. They may have created primitive lighting devices for specific purposes, then lost knowledge as dynasties fell. What is certain is that Dendera reliefs exist, carved over 2,000 years ago, depicting objects that, regardless of intent, bear striking resemblance to modern electrical technology. 10. The Lycurgus cup. In the 4th century CE, Roman glassmakers created a drinking vessel defying ordinary glass's physical properties. The cup appears jade green when light strikes from front, but when illuminated from behind, it glows deep, translucent ruby red. This dichroism results from gold and silver nanoparticles embedded in glass, a technological feat not understood or replicated until the late 20th century. The cup is small, approximately 6 inches tall, made of soda lime glass containing colloidal metals. Electron microscopy revealed gold-silver alloy nanoparticles, each approximately 70 nanometers in diameter, roughly 1,000 times smaller than a salt grain. These particles interact with light depending on size, shape, and spacing, causing specific wavelengths to be absorbed or transmitted. When light illuminates from front, nanoparticles absorb red wavelengths and reflect green, making glass appear jade. When light passes through from behind, transmitted wavelengths shift toward red, creating ruby glow. This surface plasmon resonance was not scientifically described until the 1980s and relies on quantum mechanical effects. Romans did not understand physics. They likely discovered the effect through experimentation with metallic compounds added to molten glass. Traces of gold and silver produced unexpected color changes. Skilled glassmakers refined technique, adjusting concentrations and processing methods. But the Lycurgus cup represents more than fortunate accident. Control required to produce nanoparticles of consistent size and distribution suggests empirical precision rivaling modern nanotechnology. Even today, manufacturing dichroic glass requires carefully controlled conditions, precise temperatures, and specific cooling rates. Romans achieved this using charcoal furnaces and hand tools. In 2007, researchers demonstrated principles governing the cup's color changes could be adapted for modern sensors. By embedding gold nanoparticles in glass or polymer matrices, they created devices changing color in response to chemical concentrations, enabling detection of toxins, pathogens, or biomarkers at extremely low levels. The ancient Roman technique, rediscovered through nanotechnology, had practical applications in medical diagnostics and environmental monitoring. This raised unsettling questions. If Roman craftsmen accidentally stumbled upon nanotechnology, what other advanced material properties were discovered and lost? Empirical refinement can produce sophisticated results without requiring scientific explanation. The Lycurgus cup survived because it was valuable, preserved in collections, eventually acquired by the British Museum. Countless other Roman glass objects, some potentially exhibiting similar effects, were destroyed. Knowledge of creating dichroic glass disappeared with Rome's fall, not rediscovered until modern materials science provided analysis and replication tools. If nanoparticles could be manipulated in the 4th century CE, then technological capability timeline must be reconsidered. Advanced materials are not exclusive to the modern era. They emerged episodically in cultures lacking scientific frameworks to understand them, but possessing skill to create them. And if such materials existed and were forgotten, then history is not linear progression toward greater knowledge. It is a fragmented record of rises and falls, discoveries and erasures, where the line between ancient and modern blurs, and technologies thought exclusive to our time may have flickered briefly in the past, then vanished into obscurity. Conclusion. These 10 technologies do not represent isolated anomalies. They reveal a pattern, a recurring model where human ingenuity achieved breakthroughs defying their time's limitations, only to have knowledge lost, fragmented, or suppressed as civilizations collapsed, empires fell, and expertise transmission failed. Each technology followed a similar arc: invention or discovery, practical application, dependence on narrow specialist groups, then sudden disappearance through war, secrecy, or simple knowledge transfer failure. What remains are artifacts, texts, and unanswered questions. Loss mechanisms were consistent. Knowledge concentrated in guilds, families, or secret societies vanished when groups died or disbanded. Oral traditions eroded as languages changed and cultures merged. Written records were destroyed in fires, wars, or deliberate suppression. Without institutional frameworks to preserve and disseminate knowledge, entire expertise fields could evaporate within a single lifetime. What was lost is incalculable. Computers predicting celestial events, self-healing concrete for millennia, sunlight harnessing weapons, nanostructure containing steel. These were not primitive approximations. They were functional technologies, some superior to modern equivalents, created by civilizations we label ancient, undeveloped, or technologically inferior. The tragedy is not that these technologies existed. The tragedy is they were allowed to vanish. Lost in the Antikythera mechanism proved mechanical computation was possible 2,000 years before Babbage. Greek fire demonstrated chemical warfare centuries before modern incendiaries. Damascus steel achieved nanotechnology matching material properties without understanding atomic structure. Each represents a future that could have been, a world where knowledge accumulated rather than reset, where technological progress built upon previous achievements rather than rediscovering them after centuries of darkness. Instead, civilizations rose, invented, and fell, taking innovations with them. This is not linear progress behavior. This is fragile, contingent knowledge systems collapsing when sustaining conditions disappear. The cost of that fragility is measured in lost centuries, technologies requiring reinvention, and capabilities we are only now beginning to recover. So artifacts remain: corroded gears, crumbling concrete, relief carvings, glowing cups, each one a fragment of what was once possible. Each one a reminder that history is not constant advancement, but peaks and valleys, knowledge gained and knowledge lost. Who decides which technologies survive? What ensures knowledge transfers between generations? And if civilizations as advanced as Rome, Byzantium, and ancient India could lose their most sophisticated innovations, what prevents us from losing ours? The answer is nothing. Knowledge is fragile, transmission is uncertain, and what we call progress may be only the latest rediscovery of capabilities that existed briefly in the hands of those who came before us. The ancients were not primitive. They were experimenters, innovators, and problem solvers achieving technological feats challenging our assumptions about the past. And if their knowledge vanished so completely that we spent centuries disbelieving it was ever possible, then the line between ancient and modern is not as clear as we believe. Perhaps the real question is not what technologies the ancients possessed. The real question is what we will lose when our own civilization falters, and whether anyone will remember what we were capable of.